Section: Introduction. In this section, we discuss the growing significance of machine learning models in our daily lives and the need to understand neural networks better. One fascinating aspect of these networks is their ability to generalize, meaning they can perform well on new data that they haven't seen before during training. This ability comes from their skill in learning general representations and algorithms. However, we face three main challenges regarding generalization. First, there is a lack of interpretability. Neural networks often operate in ways that are hard to understand, which is especially concerning in critical areas like healthcare and finance. Although research has improved our understanding of large language models, we still struggle to fully explain their outputs. We believe it is essential to create interpretable systems from the start, as this helps us diagnose errors, ensure fairness, and build trust in the model's decisions. Second, we encounter low data efficiency. Generalization typically requires a lot of diverse training data, leading us to question whether models can generalize effectively with less data. This is particularly important in fields with limited data, such as rare disease diagnosis or specialized scientific research. Previous methods aimed at improving generalization have focused on optimizing training procedures rather than addressing fundamental design issues. Third, we observe a phenomenon called grokking, where there is a delay between when the training loss stabilizes and when the test loss does. This delay complicates our ability to determine the best time to stop training and requires more time and resources to reach grokking. We believe these challenges are partly due to the common use of cross-entropy loss and suggest using harmonic loss as an alternative. Harmonic loss has two beneficial properties. It is scale invariant and has a finite convergence point, which can be seen as a class center. Through our experiments, we show that models trained with harmonic loss perform better than standard models by reducing grokking, needing less data for generalization, and improving interpretability. We also compare a GPT-2 model trained with harmonic loss to the standard version, finding that the harmonic model develops more interpretable representations. The rest of our paper is structured as follows. We review relevant literature, introduce the principles of harmonic loss, detail our experiments on algorithmic datasets, demonstrate performance on the MNIST digit classification task, and extend our analysis to larger models. Finally, we conclude our findings. In the related works section, we focus on improving the interpretability of neural network representations, noting that while many studies have explored how large language models form conceptual representations, significant unexplained variance remains. We also discuss mechanistic interpretability, which has become more challenging as models grow in complexity. Lastly, we highlight how different loss functions can impact model learning and performance across various tasks. Section Summary. In this section, we highlight the growing importance of understanding neural networks, particularly their generalization capabilities, while addressing three main challenges: lack of interpretability, low data efficiency, and delayed generalization, grokking. We propose harmonic loss as a solution to these issues, demonstrating through experiments that it enhances model performance, reduces grokking, and improves interpretability compared to traditional cross-entropy loss. Section: Harmonic loss. In this section, we first review cross-entropy loss and introduce harmonic loss, as illustrated in Figure A. We denote the unembedding matrix as W, which has dimensions n by v, where n is the embedding dimension and v is the vocabulary size. The representation before the unembedding matrix is x, which has dimensions n. For cross-entropy loss, we define log its y as the result of multiplying the transpose of w by x, ignoring biases. We can obtain probabilities p by applying the softmax function to y. If the true class label is C, the loss is calculated as the negative logarithm of P for class C. We refer to a linear layer combined with cross-entropy loss as a cross-entropy layer. For harmonic loss, we define the harmonic log at D as the L2 distance between the ith column of W and X. We interpret the columns of W as keys and X as a query, meaning that a smaller distance D indicates a higher probability P. We define harmonic max, Harmax, with a hyperparameter n that controls the distribution's heavy-tailedness. If the true class label is C, the loss is again the negative logarithm of P for class C. We call a layer that uses harmonic loss a harmonic layer. Since both losses end with the same calculation for loss, comparing their values is meaningful, as they differ only in how they compute probabilities. A reasonable choice for n is approximately the square root of d, where d represents the intrinsic dimensionality of the data. In large language models, we can approximate d as the embedding dimension. This approximation comes from considering an embedding initialized from a d-dimensional Gaussian distribution. The squared distance between 2 points, normalized by d, is roughly 1 plus a small term that decreases with the square root of d to keep the harmonic distance constant as d increases. We set n to be around the square root of d to illustrate the advantages of harmonic loss over cross-entropy loss. We examine two simple cases in 2D, shown in figures B and C. In both cases, we train the cross-entropy and harmonic layers using the atom optimizer. In the first case, we have 2 points, 1, 1, and -1, -1, belonging to different classes. The harmonic layer shows a quicker decrease in loss because it only needs the distance d to approach 0 for the probability p to reach 1. In contrast, the cross-entropy loss requires the log its y to go to infinity for p to reach 1. The harmonic loss stabilizes the L2 weight norm, while the cross-entropy loss leads to an increasing L2 norm that diverges. In the second case, we have 5 points in 2D, each belonging to a different class, with the red point, 0, 0, surrounded by the others, making linear separation impossible. The cross-entropy layer struggles here, resulting in a high loss plateau, while the harmonic layer effectively reduces the loss to a very small value. Similar to the first case, the harmonic layer maintains a stable L2 norm, while the cross-entropy layer's norm continues to grow. From these examples, we identify several benefits of harmonic loss. 1. It can handle nonlinear separability, as seen in the second case. 2. It converges quickly due to its finite converging point. 3. It is scale invariant, meaning scaling the distances does not affect the probabilities. And 4. It offers better interpretability, as the weight vectors correspond to class centers. The remainder of the paper will explore the application of harmonic loss in various tasks, including algorithmic challenges, MNIST, and language modeling. Section Summary. In this section, we review cross-entropy loss and introduce harmonic loss, highlighting its advantages such as faster convergence, nonlinear separability, scale invariance, and improved interpretability of weight vectors. We demonstrate these benefits through toy examples, showing that harmonic loss outperforms cross-entropy loss in various scenarios. Section: Algorithmic datasets. In this section, we discuss algorithmic datasets, which serve as effective benchmarks for understanding network interpretability due to their clear mathematical definitions. However, training neural networks on these tasks can be challenging because of phenomena like grokking, or delayed generalization, and the presence of various algorithms. We aim to demonstrate that harmonic models can learn more effective representations, use data more efficiently, and experience less grokking. We compare 4 models. 1. Standard MLP. This model uses 16-dimensional embeddings for tokens, which are combined and input into 2 hidden layers with sizes 116, utilizing the CLU activation function. 2. Standard Transformer. Similar to the MLP, it uses 16-dimensional embeddings with an additional learnable positional embedding. It processes input through 2 transformer decoder layers, each with 2 attention heads and an MLP of hidden size 64. 3. Harmonic MLP. This is a standard MLP enhanced with a harmonic unembedding layer with an exponent of 1. 4. Harmonic Transformer. This model is a standard transformer with a harmonic unembedding layer of the same exponent. We trained the MLP models for 7,000 epochs and the transformers for 10,000 epochs, using the Atom W optimizer with a learning rate of 2,000ths, a weight decay of 100ths, and an L2 regularization strength of 0.01 on the embeddings. We utilized 5 datasets for training and performance analysis. 1. In context learning, the model predicts a fourth point in a 5x5 integer lattice to form a parallelogram with 3 given points, reflecting in context reasoning. 2. Modular addition. The task involves predicting the sum of 2 integers modulo 31. 3. Equivalence classes. The model determines if 2 integers are equivalent modulo 5. 4. Genealogy learning. In a binary tree with 127 nodes, the model predicts an object based on a subject and a relation, such as parent or sibling. 5. Permutation composition. The model predicts the result of composing 2 permutations. For the permutation composition dataset, we trained the standard and harmonic transformers with an L2 regularization of 0.005, which we found beneficial for training completeness. Regarding representation faithfulness, we present visualizations of the top 2 principal components of the model's embeddings for MLP tasks. Our findings indicate that harmonic loss representations are generally cleaner and more organized than those from cross-entropy. We observe distinct representations for each task. 1. In context learning, standard models often produce imperfect lattice structures, while harmonic models consistently recover the 2D lattice perfectly. 2. Modular addition. Harmonic MLPs reliably achieve a clear 2D circular representation, whereas standard MLPs struggle with this. 3. Equivalence classes. Both model types identify groups, but standard models show more elongation, likely due to cross-entropy loss not minimizing irrelevant variations. 4. Genealogy learning. Only the harmonic MLP successfully captures the tree structure. 5. Permutation composition. The harmonic MLP yields well-separated clusters, with a notable representation of 6 clusters of 4 permutations each. Overall, harmonic models tend to produce more compact representations with fewer uninterpretable components, achieving complete explained variance in in-context learning with just the first 2 principal components. Section summary. In this section, we demonstrate that harmonic models outperform standard neural networks in learning representations for algorithmic tasks, exhibiting better data efficiency and reduced grokking. Our analysis of various models reveals that harmonic representations are cleaner and more organized, achieving higher explained variance and more accurate structural recovery across different tasks. Section: Data efficiency in training. In this section, we explore data efficiency in training. We note that while humans can learn from just a few examples, neural networks typically need much more data. Therefore, we aim to develop models that learn efficiently. Our experiments show that harmonic models require less data to generalize effectively compared to traditional models that use cross-entropy loss. This is particularly evident in in-context learning, where harmonic models can generalize almost immediately. We also address the issue of grokking, which is when a model takes a long time to generalize after achieving perfect accuracy on training data. We find that using harmonic loss reduces grokking, as illustrated in our results. Models that do not experience grokking show improvements in both training and test accuracy simultaneously. This is especially clear in tasks like modular addition, where standard models struggle with grokking, while harmonic models perform much better. Focusing on modular addition, we analyze why harmonic models yield more interpretable representations and better generalization. Standard models often fail to generalize without strong weight decay, leading to significant grokking. In contrast, harmonic models generalize quickly without this issue, and their representations form a perfect circle, indicating better structure. This is due to the properties of harmonic loss, which allows for faster convergence and clearer representations. In our MNIST experiments, we demonstrate that harmonic loss can enhance interpretability in fully connected networks. We compare one-layer networks trained with both cross-entropy and harmonic loss. Our findings show that the weights in the harmonic model align closely with class centers, while the cross-entropy model retains many irrelevant weights. For our GPT-2 experiments, we argue for the importance of pre-training language models to be interpretable. By using harmonic loss, we can create a model that develops clear representations while maintaining performance. We pre-train a small GPT-2 model on open web text and observe that it converges faster and exhibits less fluctuation in training loss compared to the standard model. To assess the interpretability of the learned embeddings, we conduct tests using function vector tasks. We create pairs of words that relate to each other and analyze their embeddings. Our results show that Harmonic GPT consistently produces better parallelograms than the standard model, indicating superior interpretability and structure in the learned representations.